Be a big deal. Although I would like you to go and actually look at the. I would like you to actually go and look at the. What do I want to say? The systems of equations where we did the predator-prey model. Just kind of look at how it works out. Kind of like look how I thought through of it. But other than that, you don't have to like follow what I'm doing on Excel or anything. It's fine. Okay. You should probably do that. All right. So here we go. So separables. Again, we talked about this last year quite a bit. We hinted at it at least. And we said, oh, look, yay, isn't this exciting? And so we did a nice, easy one. Of course, anytime you see this exponential growth, that's fine. That's one that you should recognize rapidly. You shouldn't have to think about it at all. This is exponential. You know what the answer needs to be. You know when it's all said and done, it's P of t is going to equal this kind of a thing. All right? But how to get there, we're just going to review how to get there. Okay, and then we'll see a few others today, and you'll be like, oh, I remember now. Okay. They won't all be exponential, of course, because if this was a p squared, it wouldn't be that at all. So, remember, it's separable. Separable because over here, there is no t, so first of all, that's handy. There's just the p, and therefore I can get the p over here with the dp, and I can get the dt over by itself. So 1 over p dp is k dt. And again, it's just that's just algebra. Then integrate. And so this is ln of p. Now we put that in, I usually do that anyways because that's how the big kids do it. If it's a population, it ain't negative. So, you know, just saying. Okay? Is equal to kt plus a constant. And so if you exponentiate both sides, p is equal to e to the kt plus c. And this next part is kind of a big deal. Because we'll do a lot of this year. We'll wave our hands at things with constants. And that's right here. This thing right here, e to the kt plus c, can be rewritten as e to the kt times e to the c. Right? And e to the constant is?
Another constant.
A constant. So, voila, e to the kt. Nice. And specifically, what is this c in the real world kind of thing, if it's a population? It is the initial condition, yes? It is the initial condition. So we know that p of 0 is c, right? We just know that's a true statement in the case of an exponential. Yay. Nice. Now, again, what happens to this guy up here? Look at this. Look at him. What value of p is our equilibrium solution? What value of p could you stick in there to get 0 growth? 0. So if you were looking at a solution deal, like before, 0, right? What happens if it's, well, okay, so let's assume, let's assume, all right, that k is greater than 0 for the sake of argument. Therefore, if p is positive, what happens? You get kp. What happens to this guy? Well, if this dude's positive and that dude's positive, then what happens? You get growth. Positive slopes. Okay? Now, what happens if p is negative? Which, again, weird if it's a population, but negative slopes. Okay? Now, if it was money, of course, it could decay. If it was radioactive gookumpucky, it decays, and so that's cool. But the idea here is this. And so what happens here? Well, that's if k positive. If k is positive. So we end up having a situation where we have this this and so positives and negative slopes like so. So semi-stable or stable or unstable equilibrium? Unstable. Always just going to keep bringing that back into play. Of course, what if k was less than 0? So this one would be stable. Nice. All right, piece of cake. Now, suppose you had this fella. This is another one that after a few days of doing this, you'd be like, oh, I got this one. This one's totally easy. This is logistic growth. This is always logistic. Whenever you see this relationship, it says P times something minus P is logistic. Be careful. Would it be any different if I did P minus 100? Yes. Yes. Would the solutions look similar? How to do it? Yes. What the answer is? No. So, logistic growth. Okay? Now, we're going to solve this guy. Notice again that there's just a P. That's it. There's just, notice it's just dependent variables. We call that situation when it's just dependent, we call it an autonomous differential equation. Okay? Because all you have is just dependent variables. But what about time? What about it, Rob? We're just saying this is what we have right here. Okay? Now, how do you solve this? Fair warning, it's not pretty. It's not too bad, though. I think it's one of Tatum's favorite methods he learned last year in calculus. Well, first of all, you divide over here. Now, I am not as weird as some of you are. I am going to leave the 0.2 over here. If you're weird and you want to bring it along, knock yourself out, but it's easier to leave it over yonder. Hey, I know, let's integrate. Okay, I'll do the hard side.
Okay, I'll take some salt.
But how do you integrate that thing, Tatum? How do you integrate that mess? Partial fraction. Nice. And so, I will do it down here somewhere. That's going to be 1 over P, 100 minus P, is going to be equal to A over P plus B over... I know! Yeah. It ain't terrible. It ain't terrible. All right, let's multiply by that common denominator, huh? Huh? Like so. Can I just pause for a second? Hey, how we doing? You guys feeling good about the videos? All right? You okay?
Well, this thing didn't work, so now we're looking at...
Oh, fiddle fart. Did you try the other one?
No.
What about the desktop? Was that too hard? Too far to reach?
We're just using it.
Oh, okay. Well, I'm just asking. All right, we good? Now, we end up with 1 equal. And because this is so easy, me personally, I just do it this. I don't even screw with it. I just go, hey, look, my solutions will be at 100 and 0. Yes. Yeah. So I literally just try one at a time. So if you let P be 0, you're going to have 100A is equal to 1, or A is equal to 0.01 if you prefer, whatever. And if you let P be 100, you're going to get 100B rather is equal to 1, so B is also 0.01 or 1/100th. Okay? Well, however you like to do it, I don't care. Okay? But again, you could FOIL it out, it's the same deal. But remember, when it's in logistic format, it'll always come out like this. And it will always be, you got a solution here and you got a 0 solution here. Okay? That's just how it goes. Now, interesting. So, that says that up here somewhere, I could rewrite this as the integral of I could do 0.01, 1 over P. Yeah, baby. Plus 0.01, 1 over 100 minus P. dP, and of course dP, right? All right. This one any idiot can do. What is the antiderivative of 1 over P? ln of P. Love it. The ln of P, Mr. Rome. Mm-hmm. Yeah, so some people say it, the lawn. Like, what are you, it's so stupid. Anyway, be careful on this one. Be very careful. A little substitution there. And the only reason I make sure I mention that to you is because if you do not, you will drop the negative and then you will be pissed off at yourself. As well you should be. You should do this. You should say U equals 100 minus P. And then, of course, du is negative dP, yo. Yep. So negative, come back. Negative and a positive, eh? So this is going to be a minus the ln of 100 minus P. I only write that out in a little bit longer and detailed form. Thank you. Now,
4 ones.
Again, I only take the time to write that out because that's a pretty common screw up people make. It's pretty common.
Absolutely.
All right, so a couple things. First of all, they both have a .01 here. I could times everybody by 100, right? Right? That would just make my life easier. So it's going to be I'm going to come down here a little bit. The ln of p minus the ln of 100 minus p, right, is equal to 20t plus a constant. Does that bother you? Get over it. 100 times a constant is a constant. Deal with it. Now, all right, so, oh, dude, I got to solve for p here. How in the Sam Hill am I going to solve for p?
You can combine the natural
How? How? There you go.
Oh, yeah.
It looks like poop all of a sudden out of the corner of my eye when I was looking. Exponentiate. This is correct. So it's going to be p over 100 minus p is equal to what? C. Yeah. It's right over there. Right there. There you go. Thanks.
Is there going to be a fire drill?
Someday. It's only September 12th, so probably not for 18 days. That's just a guess. All right.
Only on a test.
So, how do I get P here? What do I do?
Use your calculator.
No. You need to be able to do this. So, I'm going to go ahead and write it like this. Technically, that is just a constant right there. Okay? So you could just write C right there that made you happier. Minus P times C e to the 20t. Right? I just distribute it. Now I need to get the P's on the same side, yes? So I'm going to plus that one to the other side. Look at it. Look at it.
Boom.
And so P is simply 100 C e to the 20t over 1 plus C e to the 20t.
Will you explain that real quick?
Where? What?
The previous step.
So I plus this dude over yonder,
Yeah, I got that.
and I factor the P out.
Oh, okay.
Cool.
Now, this is not... Okay, go ahead.
So like in our initial step, right? Like the first time we multiplied by 100 on both sides.
100 minus P.
No, like
Oh
way,
my gosh! Yeah,
way
sorry.
back, way up there. And
Sure.
and you left it as 20t plus c, but now we're leaving it as a when we multiply by 100 again. Now we're leaving it as 100c.
You can't. Listen. You can, or
Or you can. Yeah,
whatever makes you happy,
Yeah.
friend. Whatever makes you happy. That's good stuff. I like it. Now what?
I
What?
guess I could ask this. It's not a question, it's a comment.
Now the reason I want to leave it there, though, there's a reason. It's not. I mean, I'm not. There's a bit of a reason for that. Now, here's what happens. This is not wrong. This is not how most people write it. Most people write it. They want to get this 100 on the top. Okay, they want to leave it on top, which means I got to get rid of this crap. If I get rid of it, I got to get rid of it on the bottom too. Yes. Now, what ends up happening is this. If you divide the top by this, and the bottom by this, oops, C e to the 20t, you end up with 100 over, now wait for it, what is 1 divided by a constant?
It's a constant.
It's a constant. Okay, Q. And then it's over, because remember it's going to be this over e to the 20t like so, right? So most kids will write it like this. That's how the big kids write it. And then this thing divided by itself is what? It's 1, right? And so most kids write it thusly. And that's how usually this is how we do logistic growth, is written in this fashion. And there's a reason for
This is
that.
just finding C for our initial, our
P of C.
original.
But no, this is the holy grail. This equation right here tells us what's happening when T is such and such. This is what your population ought to be.
Right? So if I told you a time, you stick it in, voila, done. Interesting. What happens as t goes to infinity on this problem?
It goes to 100, right?
Well, what happens here? This goes to 0, which means I got 1 on the bottom, so my population goes to 100.
It's a carrying capacity.
It is, but look at it. Check it out. In my original function, my zeros were 0 and 100, yes?
Yeah.
Those are my equilibrium solutions. So if you were to draw this out, hey, look, there's no fish. Good, there's not going to ever be any fish. Or there's 100. We talked about this being your carrying capacity up here.
Yeah.
So if you start off with an initial capacity of, let's say, you start off with 15 fishes, what's going to happen?
Yeah.
Nice. What if you start off with 112? What's going to happen? No! Yeah. And we're going to look at the graph of this thing in a jiffy. Okay? Now, what Mr. Groom did not tell you, I did not tell you a value such that I could get C here, did I? No. We need an initial condition. So let's use 15, because why not? Now, for goodness sakes, you do not have to solve for C right here. I know most of us want to. You shouldn't. Scroll back up. Because remember, this equation is the same as that equation, is the same as this equation, is the same as that one right there. Ah? They're all the same, but this one's easier to solve for C, because when t is 0, this is C equals literally 15 over 85. Yes? 15 over 85. Now, there's one little itty-bitty problem doing it that way. Just a little itty-bitty problem doing it that way. Can you see what it might be?
Is it the wrong C?
It's the wrong C.
Transformed it.
Because right down here when we divided, we divided by C right here, and we wrote 1 over that. Okay, so you be careful. So instead of being 15 over 85, it's actually 85 over 15. Okay? So right here, this is going to be 85 over 15. Okay? That's it. So just be careful of that. But in my opinion, I think maybe it's easier to go back up a ways to find a place to solve. Not always. Some people will want to do it here. And you know what? Knock yourself out. It's not like it's hard to do it here either. Because you could just as easily have done this. C. And then gone, hey, I know 15 equals 100 over 1 plus C. Cross multiply, you're going to get 100 over 15 is equal to 1 plus C minus 1, which is 15 over 15, which is 85 over 15. Ta-da! And the crowd goes wild. Okay? Now, let's go ask the great Desmos.com what's up. So, Desmos.com. Go. Go, you hippie.
We could try to graph it in 3D too.
I don't know. We're not going to graph it. There's no reason to graph in 3D. It doesn't make any sense to graph in 3D. Now, 1 plus, what was it? 85 divided by 15?
85 divided by 15.
E to the negative 20x. Bam. Okay, cool. Now,
That goes up there fast.
okay, now, let's drag it out a ways. Yeah, no, it goes up fast. Why does it go up so fast, Mr. Groom? Because our growth rate is ridiculous. Right? It's absolutely ridiculous. So it doesn't take very long. But look at this thing right here. Let's stretch this dog out a ways on the x-axis. So let's start from, like, say, 0 here. There. Okay? So something along those lines, if you stretch it out over a time period. But again, notice it gets up there in a big hurry. Gets the job done. The only difference between this problem and a different one, if I have a different growth rates, so we had 0.2, if we had like 0.1, 0.05, or something like that, it would stretch it out longer, same thing. But
It's just approaching 100, right?
the approaching 100. Yeah.
Is there a significance on what the y-intercept is?
It's the initial population, yeah.
Is it?
Yeah, exactly. Ta-da!
And you're like, well, wait, what if they put too many fish in to start with? Mr. Green, what if there's 150 fish in there? I don't know. Let's see. Let's see what happens. Well, this would be 150, right? Right? So, yeah, And then I need to subtract 150 over 150 like so, because that's 1, right? So it'd be negative 50 over 150, which is negative a third, right? So then the formula would just become this, like so.
Yeah.
It would still go to 100 as time goes to infinity, yes? But, well,
Now, please.
it was literally where I was going, but that's cute. Not fast enough, apparently, Mr. Groom. I'm getting there, yo. Bam. But again, here is your equilibrium solution up here, right? That's one of our equilibrium solutions. But again, we came at it from the bottom side like so. We came at it from the top side like so. And what do we get? Oh, yeah, stable equilibrium.
So where does it end at the top?
What?
Where's it at the top? It doesn't matter then. Where's it at the top?
Oh, it just keeps going up?
So population always wants for a stable equilibrium.
It will always go toward equilibrium, Mrs. Crack, yeah. If there's a stable equilibrium, it comes toward stable. It doesn't mean, listen, if you just had an exponential, but Corey, if you just had exponential, it wouldn't go to an equilibrium, but it would have come from an equilibrium. Right?
So aren't like the functions where it has that S-shaped form, aren't those called sigmoid functions?
That's logistic functions, man. This is a logistic function. This thing right here is a logistic function. That's how that's just logistic function.
Doesn't the hyperbolic tangent also do that?
Arc tangent looks like that.
Arc tangent has a strong.
Arc tangent looks kind of like
That
that.
was 100 just because you just.
What? What?
In
The original equation, Mr. Green, there's just 100 in there.
100. So no matter what you.
If it had been 200, then the line would have been at 200. Exactly right. Exactly. Now, let's try this one. Because you're going to say, oh, this one looks very similar, Mr. Green. It does. It's not. At all. Oh my gosh, it's like almost the same problem. Notice that your equilibriums are in the same spots. 0 and 100. But this is weird. So check this with me now. Obviously we got a 0 at here, right? And 100. So let's just look at them this way first. We'll analyze it thusly. So, again, if P is between these guys, what's happening? That is, let's say 50. Well, that's positive. This is negative. We got negative slopes in here. So we're doing some of this action. Negative slopes. If we had like 200, these are positive slopes. So we're going away. And what if they're negative populations? Well, this would be negative. This would be negative. So positive slopes. Oops, slopes. So we're coming like that. Meaning that this fella here is what? Stable and he's unstable, yes? Or is he semi-stable?
No, it's unstable.
He's going away, he's going down. Yeah, he's unstable, yeah.
Is it possible that we could have more than one stable equilibrium?
Yeah, it's possible.
So then what would
You'd have to have like a cubic function
would
to
it
pull it
depend
off.
on like what the starting population was to figure
Yeah.
out whether it would go up or down?
Yeah, in an autonomous stage. Now, if there was a T floating around there, that's a little different story. But yeah, if it's autonomous, yes. What?
Do these populations ever have like a buffer zone? So like what we're saying is currently it's like if it's on this line.
Keep in mind that in your fish population, the carrying capacity might be 100 fish. There'd never be 150 farms. There's 95. The next year, there's all of a sudden they breed too much, and then because there's like sufficient nutrients, and they all die off and get back under it again. And that's where everything wants to tend towards. Okay, life never is exactly perfect, but mathematically, yes. Right? It's just like when you spill some plutonium right here. It's never going to be gone mathematically, but eventually you wouldn't be able to see it or detect it even because it would get small enough. It would take a long time, but theoretically, yes. But it would never be 0. Okay? So, theoretically.
I was talking about like kind of a zone where it's not heading towards anywhere.
No. It's always going to be going somewhere. Okay? There's just the equilibriums where it's not moving at all. So, this guy here, obviously, is a little bit different. It's similar, of course. Still going to be partial fractions, of course. So 0.01 t plus a constant. This time I don't really have to do a whole lot of math to this one. I think it's going to be exactly the same as the last one, except what?
I think it's going to be, well, it's going to be 1 over, I'm going to do it this way. I'm going to do it, so A over P. Oops. So as you can see, it's still going to be 100, I think, on both of them, yes? What am I looking for here? I couldn't think of what I was doing. Someday you too will have that same thing happen to you.
Yeah, it's already.
So 1 equals, okay? So if you let P equal 100, if you let P equal 100, you're going to get B is 0.01 again, right? If you let A equal, or P equal 0, be careful right there. What's going to happen is what? This is 0, it's going to be negative 100, right? So A is negative 1/100. And B is equal to 0.01, right?
Yes.
So just be a little careful of that. But notice what happens when you do this time. You're going to get 0.01, 1 over P, plus 0.01, not negative, sorry, plus 0.01, 1 over P minus 100 dP. So of course that's negative 0.01 ln of P plus 0.01 ln of P minus 100. This time I didn't have to change the sign on that guy because of, you know, it didn't need it, right? Is equal to, and of course that's 0.01 T plus a constant over here. I'm just going to go ahead and times everybody by 100 again. Okay. And we're going to do the same thing we did last time, except be careful. So when you exponentiate, you're going to get c e to the t. So that part should look very familiar. Notice these are just backwards. Okay, which this problem is actually easier to solve for than the last one, because you multiply by P and then play musical chairs. But it's a very wildly different function when you graph it. It's wildly different. Wow, is it different. I'm going to put the 100 over here because I don't really dig negatives. Right, like so. Nice. Now, if you think about this as a population of critters of some type, okay? Something nasty, cockroaches or some such, I don't know. Something kind of gross stuff. What happens in the original problem up here? What happens if I have more than 100 cockroaches? Wildly. What happens if I have less than 100 cockroaches? It goes to 0. Wait, that's weird. Either they're going to go extinct, or there's going to be a problem. The problem is usually referred to as doomsday.
So what if you have 100? Then you have like a 50-50 chance of.
Now, if you're 100, you don't, theoretically, nothing changes. If you're at 100,
right.
because you're equilibrium. Now, interesting. Let's pick an initial population. Let's do P of 150, sure. So P naught is 150. Sure, why not? It's a good time. Why not? Now, I didn't change what C was on this case, right? I didn't flip it over at all, right? I didn't change C. Now it's this C. So I'm going to come back up to this deal to solve for it, I think, this time. But you can solve for it down here if it makes you happier. It's whatever makes you happy. Really don't care. So, but if I did that, I would just go 150 is equal to, and then I would do 100 over 1 minus C, I guess, yes? Right? And so then 1 minus C is equal to, this is 2/3 because it's 100 over 150. Right. And then play musical chairs, so C is 1/3, looks like, yes? Yeah?
Yep.
Nice. So 1/3. What? This is negative. What could happen to this deal at some point? This thing could what? This bottom could equal 0. It could equal 0. And that would be a problem. And what happens when your denominator goes to 0? You get a asymptote. But the question is, where does that occur, friends? I don't know. Right? Equals 0. That's what I'm interested in. Not where, when does it occur? So 1 is equal to 1/3 e to the t. 3 equals e to the t. T is equal to the ln of 3. Whatever that is. What is that? ln of 3 on your calculator.
It's like 1.1.
No, it's not. Yeah, 1 point. So if this is in years,
1.098.
1.09 years, we are going to have a problem. Okay, that's doomsday. Now, let's graph this thing. What was it on top?
Math is
What was my function? 100? Oops. Wait, stop. 1/3. There it is, baby. And we seem to have reached an asymptote. And that's the line about x equals 1.4. Oops.
1.09.
Or, yeah, x equals, 1.09. That's pretty close. We're getting close to it, whatever. Now, but notice that we're only at population at 800. That's not really doomsday yet, but it's getting there. Okay. Now, what happens if we had a different initial value, of course? Well, it's a different number, of course, Mr. Grimm. That's a stupid question. I know. But let's look at it. So what happens if this is, 50 or something instead? Sure, why not? Well, if it's 50 instead, then this is just 50. And then that's 2, right? Right? So that would be, C would be -1. Right. That's right. So then this becomes plus, like so. Nice. Hey, when does this bottom equal 0 now? Bruh, it doesn't. It doesn't. Which is what's happening. Because as t gets bigger, the denominator gets bigger, the whole thing gets smaller. So we are going to have the same thing. It's extinction, explosion, extinction, doomsday. That's the idea here. And again, a minus sign is the only difference it makes. Yes? But doomsday, extinction, explosion ones, the doomsday not so much, but the extinction part of it does happen. Okay? So a situation where different population of some kind of critter, right? So it's a deal, if you got into wildlife management stuff, you can see some of that happening, right? You see a lot of logistic growth with harvesting. So we're going to do a lot of that coming up. How many fish, how many deer, whatever can you harvest without hurting the population at all, based on their growth rates and their habitat and everything. But extinction is one where you have to be a little careful of, because in the case of an extinction deal, it's a very tenuous situation. You tweak anything just a little bit and then you've got problems, right? So I can't give you an example of one, but the doomsday, not so much, all right? Mathematically, yes, but the extinction deal is a real factor on something. You're walking that tight line, it's the precipice there. Anything just too much, if one, just any little thing happens, see it by. Keeps going. Yeah.
So that means like us doing this thing. So if we had a logistics function that we had, then we'd be able to work backwards too and then find the differential equation and like answer them. Could one do that?
Okay, that's not a bad question. So if you had a function, can you find a differential equation? Yeah, they agree with it. Yeah. But see, that's not how differential equations work. Differential equation says we know the rate at which things are happening, and we can maybe even build a function for that. And then we can work backwards to see where it came from. But there's nothing really new under the sun for the most part. Like, I want to become a wildlife guy. Okay, good for you. Well, when you're studying here's your basic function you deal with all the time. In fact, you're not really doing differential equations on that, but you might tweak a few parameters here and there, and okay, that's neat. But mostly it's just, showing up doing the thing. But it's the same thing is true for any kind of engineering stuff. A friend of mine works at Boeing. He doesn't really do any calculus per se. He just I need to create this deal. So he just fiddle parts around with this and that and makes a new deal. But it's not like he's doing any calculus in differential equations. Yeah.
So then So we have like taking implicit derivatives with calculus 1 and calculus 2.
Sure.
Is that like reflected in differential equations via like non-separable differential equations? Are they like opposites of each other?
No, not exactly. Non-separables are just, they're kind of a different breed of cat. So, hey, so separables we do first. We'll do all kinds of non-separables later on. So, like one we'll do later on is, it's very common, is the linear ones. If it's not separable, it's linear. So, the idea is that after a while you look at it, you go, oh, that's that kind, you can do this and such. Oh, that's this kind, you can do this and such. This one is separable because, again, I can get the t's and the y's apart because they're either multiplied or divided by each other. So, I will leave the t where it's at, and I will put this one business on the other side, like so. And 1 over t dt. Don't forget your dy, stupid. There you go. T. Let's integrate this beast. So, oh, geez, this is tough. ln of t plus a constant. I'm only going to put my constant on that side. I want to leave my y with no constant. What's this? What's this crap about? I don't know. But I do know that I should do u equals 2y plus 1. du is, well, I only have a half of a dy, so there you go. So I'm going to have a half ln 2y plus 1. Nice. So, I'm going to multiply both sides by 2. So the ln of 2y plus 1 is 2 ln of t plus a constant. Let's exponentiate, shall we? Oh, geez. How do I exponentiate this garbage? Wait, I know. This fella right here, from whence did this 2 come? It came from up here, did it not? So let's put it back from whence it came. So it's e to the ln of t squared. What happens to e to the ln of t squared? You get t squared. T square. And then, of course, listen, e to the c is just a constant. And where does it go? Out front. Nice. This is where logs start to freaking matter. And so, you're going to get c over t squared minus 1 all over dos. Like so. This is y of t. That's nice. It is a general solution. If I want a particular solution, I need to give you a value. Again, we frequently throw things at you like of 0, but there's no reason why I can't do this. Yes? Why not? Okay. And so 17 would equal 9c minus 1 over those. Be careful. There is no reason to solve it from here. Why are you solving it from here? That's ridiculous. Solve it from right there. Don't be weird. Right? What? Wait, what? C, because it's 3. 3 squared? 3 squared? I think I'm going to go here, because I think I find that one to be easier, maybe. And so, but you know, whatever. So it's 35 over 9 is C, is that right?
Oh, yeah.
Yay! And the crowd goes wild. Okay. What?
You could make it 18.
So it is 3.8888888888888. Nice. Okay. Now, so, okay, that's it. So that's that. That's all fine and good. Question, because Brandon brought it up. Do this for me. What is, you said it was 3.88888888888. No, I don't want to do it that way. Screw that. What did I say was 35? So I'm going to say 35 over 18 t squared minus a half. What? 35 over 9 over 2.
Oh, got it.
So, but look at this function right here. Check it out. Check him out. He's pretty cute. He's a pretty nice guy. What's the derivative of this speller? What's the derivative?
35.
So y, so wait for it. Y prime is 35/9 t. That's weird. That's really weird. Strange. Our original function was 2y plus 1 divided by t. But what's y? I feel like y is equal to 35 over 18 t squared minus f. So if I take 2 times that, I'm going to get 35/9, right? T squared minus 1 plus 1 over t.
Oh man, I see it.
And then, and then, and son of a gun, you end up with 35/9 t, right? Which is where you ended up with the thing. So the question is, can you get there? Yes. Can I tell from what this is what I'm going to end up with an answer? No. With exponentials, yes. Logistics, yes. Some of the ones that are pretty obvious, yes. This one, no. But it's not very hard either. Okay. I'm going to do one more quicko, and then you're going to have some of these on your assignment tonight. Fair warning, you may run into a few that kick your tushikins. It's okay. Don't worry. Don't cry. Just come get some help. It's fine. Yeah. So, yeah, let's do that one. Oh my gosh. First of all, it's autonomous. Yes. Because it's just the dependent variable. Is it separable? Yeah. Can I get these y's on that side? Yeah, I can. Yeah? Nice. All right, so any idiot can do this side, yes? How do you integrate that thing? Well, let's let u equal this feller, yes? So negative a half of a du is y dy, right? So then I really have 1 over y basically, yes? So ln come into play again. I'll show that step. So it's negative a half 1 over u du is what we end up with. So it's the negative a half ln 1 minus y squared. Yes, there we go. I feel like I'm going to times both sides by negative 2. I keep forgetting that 1. So negative 2t plus a constant. That bothered me as a child. Well, a high school to a college child. Multiplying by a negative. It's just a freaking constant. Let it go. It'll be fine. I promise. Okay? Now, exponentiate. And we should end up with c e to the minus 2t, correct? Now this is where it gets a little wonky, peeps. 1 minus c e to the t 2t, negative 2t, right?
Yes.
There we go. What is going to happen here? You're going to do this, are you not?
It's gonna get it back to
No. It is going to be just hunky peachy.
We scrolled a little bit.
Yeah, sure. Here's my question though. How many freaking answers do you have here? Technically you got 2, technically speaking, yes. However, we were told initially that is y of 0 was negative 2, right? Y of 0 was negative 2. So up here somewhere you could do it. So it's going to be 1 minus 4, because y was negative 2, is equal to c. Means c is equal to negative 3. Which means this is going to be this business right here, plus 3, right? Yeah. Now, how do I know if it's the positive one or the negative one, Mr. Groom? That's a good question. So for today, you're just finding it out. But in a couple of days, we're going to talk about the fact that, how do we know if this is the only unique answer? We're going to spend some time talking about that in a couple of days. All right? So But for right now, you just solve it. And, oh, yeah, I got it. Yeah, good for me. Okay. But in a few days, we're going to talk about how do I know if this question has a unique solution or not. Okay, so we'll spend quite a bit of time on that. But just today, that's all you'll be doing. Be careful. You may see one or two like this, where you might see, and I just throw it out there for you. Or no, like that. Oh no! Factor T out for crying out loud. Okay, there you go. And I'm not saying that's what you'll see, but you'll see maybe something like that where you have to do some factoring first, because initially it is not looking separable. But now it's multiplication, now it is separable. Okay, so you might do a little bit of work first. Okay? Yeah, what?
So what would happen if C, we found C to actually like be negative? Because then if the square root is of a negative.
Well, it would only exist over a certain population.